Okay, so today we were supposed to be talking about polynomial division, and so we're going to do this by video instead. And what I want to do is do a really quick review of elementary school math. So I want you to think back and make a connection between what you already know about numbers and how that can relate to polynomials. So for example, you might have been in elementary school when they were trying to see whether 2 divided into the number 10. And you called 2 the divisor, you called 10 the dividend, and you tried to see whether you could find a number that when you divide it into 10, you ended up with no remainder. So in other words, you pick the number 5 because 2 times 5 was 10. And if you took 2 times 5 and you multiplied them and you subtracted, you would have captured the entire number 10 in these two factors, 2 times 5, without any remainder, just 2 times 5. So what that looks like if you connect that to what you know about Math 21, is because x plus 2 times x plus 1 is x squared plus 3x plus 2. That's something we know. So you learned how to FOIL. You made that connection that these two were called factors. Just like 2 and 5 are factors of 10 because they multiply to 10. X plus 2 and x plus 1 are factors of x squared plus 3x plus 2 because they multiply to that. And what we're going to make our connection with is you could actually take x plus 2 and divide it into x squared plus 3x plus 2, just like you can take 2 and divide it into 10, and the other factor should appear up here as your answer, which is called the quotient. So based on what I'm saying here, we should be able to divide one polynomial into another polynomial if it's a factor and end up with the other factor up top, which is what we're going to do. But what happens if it's not a factor? Okay, so let's think about that in math, in arithmetic. If you were trying to take 7 divided by 2, well, that's going to look like this. You're going to see, I've come up with a number, then when I multiply it by 2, it becomes 7. And I can't. 3 is as close as I can get. That's only 6. So when you don't capture the entire number with your two factors, you don't capture the entire dividend, you end up with what you would call a remainder. And when you were first learning this, you might have done something like this: 3R1, 3 remainder 1. That's not a really good idea because you don't really know what that 1 means. All you know is that you've got 1 left over. So then you started to use notation like this. Well, 3 and 1/2. So 7 halves is 3 and 1/2. And that told you that this 1 means that you had 1 left when you were trying to divide by 2, which is very, very different than having 1 left when you're trying to divide by 3, right? I mean, that's still the same 1, but it doesn't mean the same thing. Because if I'm trying to divide by 3, what I actually have left is a third, because I was trying to break this thing into pieces that were size 3 versus size 2. So this notation is really important, but the other thing that I notice a lot of people don't realize is when you say 3 and 1/2, you literally mean 3 plus 1/2. And 3 and 1/3, 3 plus 1/3. So this is like the extra that you have left over after the division, and it's like you would have to add it back on to get back to the original number. So if you hadn't thought that way, you want to think that way because we're going to end up dividing and having remainders. And we're going to have to know how to deal with those remainders. So if it isn't a factor, we're going to know because when we divide, we're going to get a remainder that's not 0. So putting all that together now and looking at it in terms of algebra, I just have a little blurb up here that in arithmetic, we would call 2 and 3 factors because they multiply to 6. And if we only knew one of the factors, like if somebody told me that 3 is a factor of 6, to find the other one, I would want to divide. So I'm going to use that inverse operation of division. Well, same kind of thing here. If you have a polynomial and somebody tells you that, hey, the number 2 is a 0 of that polynomial. Well, I noticed that when I plug 2 into this polynomial, I get 0 out. Well, that's going to mean something really important for us now. 2 being a 0, we're going to have to think backward and say, how is that possible that I know that when I plug 2 in I get 0? It must be that if I factored this thing, x minus 2 would be one of the factors. That's the only way 2 could be a 0, is if x minus 2 was one of the factors. So we're thinking backward. In Math 21, we went like this. We said, oh, I factored this polynomial, and I know that -1 is a 0 because this is a factor. Well, now we're going to go backward. Somebody's going to say, hey, -1 is a 0, and you're going to say, oh, that means x plus 1 is a factor. We're using the reverse logic to try to look at polynomials that were a little more complicated, and I really don't know how they factor. So getting a 0 can help me start the process. But the way that I'm going to get the other polynomial, this some other polynomial, the mystery that I don't know, is the same way I would do it up here. If somebody told me 3 was a factor, I would divide to find 2. If I know x minus 2 is a factor, I'm going to divide x minus 2 into the polynomial to figure out what the other factor is. And what this division looks like when I'm doing it with polynomials is a lot like what it looks like if I'm dividing into an integer into another integer. So I'm going to put that next to it, and we're going to sort of compare what we're doing here. So if I were doing this division, I would try to find a piece of the beginning of this number that 2 could divide into. So I would try to divide 2, not into the whole thing, but only into this part of it. So I'm going to divide 2 into 17 and say that'll go 8 times. And then I take 8 times 2, and I realize I only captured part of that 17. So I need to know what's left. That's what the subtraction does. So let's do that over here. X minus 2, I can divide it into this part because I know that I can divide x into 6x cubed. So we're really just looking at the beginning piece of this and the beginning piece of that. Just like we looked at only the 17 and the 2. So x into 6x cubed is going to go 6x squared times. So if you're not clear about that, this again is a Math 21 idea. Dividing monomials, you could subtract your exponents. So I know that x can go into 6x cubed, 6x squared times. Why am I putting it here? Because I want to keep all my degrees the same in a big vertical line. So I'm going to put it over here instead of over here. But then, just like I took 8 times 2, I'm going to do that here, but I have to remember to distribute. And that's why I underline these two, because I'm actually going to end up with 6x cubed minus 12x squared. And that's going to be able to be subtracted from these two, just like 16 was subtracted from these two numbers. So I'll subtract. These will go to 0, which I knew they would, just like my ones did. And negative 19 minus negative 12. So I have to be really careful now that when I subtract, I end up actually subtracting with distributing the negative. So I'm going to end up with negative 7x squared when I subtract these two. So now we're at the same place. The next step here is to bring down that 6 that I haven't divided into yet. And then take a look again and try to divide 2 into 16. So I could do that and get 8. And then I'm going to do, again, 8 times 2 and subtract. So over here, I need to bring down this 16x. And then I'm going to take x and see how many times it divides into negative 7x squared. I'm going to get negative 7x. But what I'm going to have to write down is minus 7x. Because these numbers are going to be put right next to each other and assume that I know what that means. If I put these right next to each other, it's going to look like multiplying. So when I say it goes in negative 7x times, that's really minus 7x times. I'm going to distribute negative 7x squared plus 14x. Negative 7 times negative 2. And subtract. These will be 0. And this will be 2x. So I'm at the same point. The last thing I do over here is I bring down the 4 and I try to divide 2 into 4. Goes in twice. 2 times 2 is 4. And I realize it went in evenly, which I knew it would. 2 would divide into that evenly. But that means that 2 is a factor of 1,764. And it also means that this is a factor of 1,764. It means they're both factors. So the 0 remainder was really, really important. So let's see if I get a 0 remainder over here. Well, x goes into 2x 2 times, so I had to say plus 2. 2 times 2x is 2x, and whoops, I forgot to bring down my negative 4. Can't forget that. 2 times negative 2 is negative 4. Bingo. I got a 0 remainder, and a 0 remainder means that x minus 2 is a factor of the polynomial, I'm just going to say, instead of writing all that. And it also means that 6x squared minus 7x plus 2 is a factor. So that means, I should erase this because I'm running out of room. This other factor, the mystery factor that I needed to know, is right there. 6x squared minus 7x plus 2. So I can write this polynomial as that divisor times that quotient. Just like I can write this, 1,764 as 2 times 882. The exact same reason. A remainder of 0 means that this times this is that. A remainder of 0 means this times this is that. But I could go even further because I know how to factor this. This is just a quadratic, right? An x squared. I learned how to factor that in Math 21. So the new part is I'm taking something that I wouldn't know how to factor in Math 21 because my only option was something like this, if you remember, was grouping, and I can't group that. So not being able to group it, I needed this other strategy that I have, and then I can look at this and say, well, I know how to factor that. That's 3x and 2x. And 2 and 1, there we go, minus and minus. So make sure that you're practicing your factoring because you have to know how to do that as well to get it down to 3 factors. Sort of like I could take the number I had up here, right? The 1,764, I called it 2 times 882. I could say 2 times 2 times 441. All right, I could write it as 3 factors instead of 2, and that's what I'm doing here. When you multiply them all up, you'll get back to that. All right, so I want you to pause the video for a minute, and I want you to try this bottom one on your own, because watching me do it and you trying to do it are two different things. So pause and try it. I will do it and you can check yourself, and then we'll move on to the next idea. I can get this all factored to x minus 4 times x minus 3 times x plus 1. All right, so moving on to the next page, we've got to think about, well, wait, what happens when polynomials don't factor? So if we think back to the numbers I was talking about before, 2 isn't a factor of 7. So what does that mean? Well, I still can take this thing that we call improper, and I can make it proper. So improper means that the 7 is larger than the 2. So I still can do the division and come up with a number like 3 1/2, where the 1/2 now is a proper fraction. They mean the exact same thing, but sometimes it's easier to think about it this way. So I know how many times 2 went into 7, even though there was a remainder. And this is what I'm going to try to figure out here. I try to divide here. I try to divide x plus 1 into x squared plus 3x plus 5. I'm going to go x dividing into x goes x times. X squared plus x. Subtract 2x plus 5. X goes into 2x 2 times, so I say plus 2. And I get a remainder of 3 when I subtract. So that's telling me that x plus 1 is not a factor of this. There's a remainder. But just like I can write it, I can write this 7 1/2 using the information I got. It's 2 times 3, but plus that extra 1 that I have. That's how I get the 7. It's 2 times 3, but there's an extra 1. We could do that same thing here. It can be x plus 1 times x plus 2, but there's an extra 3. So I have to write that on the end, plus 3. And that's where this division algorithm comes from. That you can take polynomials and divide them. As long as you're dividing, the divisor itself has to be a lower degree than the dividend. So x plus 1 was a lower degree than this dividend. You're going to end up maybe getting 2 expressions you can multiply together, and then if there's a remainder, you can add it on to the end. And if that remainder ends up being 0, then that means that you had factors. If it's not 0, then you don't have factors. Another way to think about that, though, is, to me, a better way to think about it, is that you can take an improper fraction, right? You put a rational expression where the numerator has a higher degree than the denominator. And you can write it as a polynomial plus a proper fraction. Like the 7/3 is the 2 plus the 1/3. Or in the example we had up here, I could write that when I take x squared plus 3x plus 5 and I divide it by x plus 1, I get x plus 2, which is the divisor, plus the remainder over, x plus 2, which is the quotient, plus the remainder over the divisor. So I'm thinking that this is improper, but I can write it like this and it will, sorry, you're not seeing that, it'll be proper. It's the quotient plus the remainder over the divisor, which is exactly what we do with numbers here. So this is another way that we can express an improper fraction in terms of polynomials. And so what we mean by improper, I just have in the box there, the degree of the numerator is greater than or equal to the degree of the denominator. So there's a couple tips for this long division. We need to have the polynomials in standard form. And that means that if there are missing terms, we need to put placeholders in. Because if we don't put placeholders in, our division is not going to work out. So by placeholders, I mean x cubed minus 1. We want to think about it as x cubed plus no x squared terms plus no x terms minus 1. So hopefully you already know the answer to this. You should know the answer to this. If you take x cubed minus 1 and you divide it by x minus 1, that would have been a Math 21 problem because we know how to factor this. We know that it factors like soap. So x minus 1, we use same, opposite, always positive. We square our x, we multiply these together, and we square our 1. And we know then that since these are common factors, as long as x isn't the value 1, we could divide, and there's our quotient. So I already know the answer, but let's see what that looks like in long division. Without these placeholders for the missing terms, I'm not going to be able to long divide. So with them, you can see why they're necessary, because when x divides into x cubed, it goes in x squared times, and I need a place to put that. And I also need an x squared term, because when I distribute, I'm going to have to subtract this from something. So without that, what am I going to subtract it from? They need to be like terms. So, oops, that's a cubed. Those are going to subtract to 0. These are going to subtract to x squared. I'm going to bring down my 0x and do it again. X goes into x squared, x times. I'm going to distribute, and I'm going to subtract, and I'm going to bring down my 1. X goes into x one time, and 1 times x minus 1 is x minus 1. I get my 0. That means I have a factor, and I already knew that though. Right? I already knew that that was going to be the factor. It's not a surprise. So putting in placeholders is an important thing to do. Otherwise, you're going to mess up your division. Okay, I want you to, again, turn off the video for a minute and try this division problem. But what I want you to notice is we're going to be dividing by something a little bigger this time. Our divisor is going to have 3 terms. But that's not going to change the process that you're going to go through. So take a minute and try that long division on your own, and then you can turn it back on and check your answer. let's just be 3. That's 9. And I need to bring down all of these. And I'm going to subtract and get 11x minus 4. Oops, messed up. Try that again. So it often happens that I'm rushing and I mess up. So I'm going to try that again. So instead of trying to figure out where I went wrong, it's sometimes helpful for me to just get a blank slate and talk myself through it. All right, so x squared goes into 2x to the 4th, 2x squared times 2x squared times x squared is 2x to the 4th, plus 2x squared times 2x is 4x cubed. So I was right. Subtract, bring down. Now I have to bring down. I did it again. All right, I forgot to distribute to all 3. So 2x squared, 2x squared, 2x squared. There we go. That's what I was missing. Subtract. All right, 0, 0, not 0. Then I have to bring down my 5x and bring down my negative 2. So I can do it again. X squared into 3x squared. And 3x squared, 6x minus 9. All right, I subtract, I get negative x. I subtract, I get 7. There we go. So, because there were 3 terms here, I needed to bring down 2 terms every time so that I could have 3 here to match the 3 there. And I'm not showing you that. Sorry about that. So, I end up with my remainder, and I end up with my divisor and my quotient. So this means that when I divide this into that, I end up with 2x squared plus 3. And then I have my remainder that I want to put over my divisor. So this divided by that is improper. This is now a polynomial plus a proper fraction. So I messed up, but hopefully you can figure out, if you did too, where we got together. What I messed up with is I forgot to multiply by all 3 of them, so then I didn't have what I needed here. All right, so good news. There is a shortcut to all of this. You see how messy it can get. I had to erase and start over. You can deal with some of the messiness as long as you're only dividing by x minus or x plus a number. So there's no shortcut here. When I'm dividing by x squared, it's got to be that messy. But if I'm only dividing by a linear, this is called a linear factor because x is to the 1st power. If I'm only dividing by a linear factor, there's a shortcut. This is the picture from the book. That may or may not be helpful to you. You may want to look back on it after I've gone through this example, and maybe it'll make more sense. But to me, the example here will hopefully cement things a little bit. What you want to notice is we were doing the same thing over and over and over again, and we were trying to stay in columns. But the hardest thing here was it was subtraction every time. And so synthetic division actually deals with that. It makes it addition every time. And the way it does it is it looks at this factor and turns it into the 0 that this factor gives you. If x plus 3 is a factor of this, then negative 3 will be a 0, or a number that when I plug it in, it makes this 0. So it takes the 0 from the factor, put it in a little box, and then what we're going to do is just keep track of all these coefficients. Instead of all the x squareds and the x cubes, we're going to just put the coefficients here and stay in columns with those. So you got to notice there's a missing term. If you have a missing term, you can't miss that coefficient. So I want to use the number 1 as the coefficient of x to the 4th. I want to stick a 0 in as the coefficient of x cubed. Then I can put my -10, and then my -2, and then my 4. So all the coefficients are going here and lined up correctly. Then the strategy is I'm going to bring down whatever this first coefficient is. I'm just going to bring it right down and put it here. I'm going to take the -3 times the 1 and put the answer here. And this is where the addition comes in. Instead of subtracting, I'm going to be adding. Because I made that a -3, I can say plus -3 instead of -3. And that's going to give me -3. -3 times -3 goes here. And again, add. So -10 plus 9 is -1. -3 times -1 is 3. Put a plus here, I get 1. -3 times 1 is -3. Put a plus here, uh-oh, I have a remainder. So what that means is this wasn't a factor of that. Because if this was a factor of that, this would be 0. So x plus 3 is not a factor of my polynomial. But I still can write my answer as proper now. Okay, I'm not going to be taking this divided by that and making an improper fraction. What I'm going to end up with is this polynomial plus this remainder over that divisor. So I'm going to do the exact same thing. It's just that I don't have all the x's to deal with. So I'm going to say plus 1 over what I was dividing by. And then this is a polynomial. Well, how is that a polynomial? You've got to back yourself up 1 degree from where you started because you divided. This is now your x cubed coefficient. This is your x squared. This is your x, and this is your constant. So your polynomial is x cubed minus 3x squared minus x plus 1. So getting good at this, and it took me a while to get good at this after I hadn't seen it for a while, getting good at this is like getting good at dividing 2 into 7 and following the pieces. Same thing. This is just an alternative way to do the division. That gets, the faster you get at it, the better, because later on it's going to be really helpful. So you want to practice it, but you want to be thinking about the bigger picture as well. And I will see you on Friday.